Greetings of the day to all of you. Welcome to the lecture on space vector modulation of a 3-level NPC, or as you may call it, a neutral point clamped multi-level converter, also called as a diode clamped multi-level converter. Given here is the diagram, the circuit diagram of a 3-level NPC with only phase A shown in picture. You also have, if it's a 3-phase converter, you may have phase B and phase C, which are very similar to phase A over here. We have discussed this in the previous lecture, that the DC bus is split with the help of two capacitors into say equal capacitor voltages VDC by 2 each, and then the middle point is connected to the legs to the middle points of each of the switches through a clamping diodes. Each leg is clamped through diodes to this middle point. Similarly, phase B will also be clamped to the middle point, and phase C will also be clamped to the middle point through their respective clamping diodes. Each leg has 4 switches, so if this is switch 1 and this is switch 2, we also know that they will have complementary switches S1 dash and S2 dash, which means that S1 dash is a complementary switch of S1 and S2 dash is a complementary switch of S2. If we talk about the switching states, we have already discussed them before. For each leg, there are 3 switching states. The first switching state is when both S1 and S2 are on. Both of them are on, which means that if you see the pole voltage with respect, the phase voltage with respect to the pole voltage, it is simply equal to plus VDC by 2. So in this case, the voltage is plus VDC by 2. And the other state is when S2 and S1 dash are both conducting, that is the middle 2 devices are conducting. In that case, if the current is positive, then the diode and this switch will be active, such that VAO will be a short circuit, or you can say that whenever S2 and S1 dash are both given a pulse, then at that time the pole voltage VAO is 0. Similarly, the last switching state for this leg is both S1 dash and S2 dash are on, which automatically means that S1 and S2 are off because these are complementary, and in this case minus VDC by 2 directly appears at point A with respect to point O. So you have a 3-level pole voltage, which is plus VDC by 2, 0 and minus VDC by 2. Each leg corresponds to 3 switching states. So you have 3 switching states for phase A, 3 switching states for phase B, and 3 switching states for phase C, which makes it a total of 27 switching states. If you remember and compare it with the standard 2-level voltage source inverter or 2-level VSI, there you had a total of 8 switching states. So there was one leg had 2 switches, so 2 switching states. So there were 2 switching states into 2 switching states into 2, that is a total of 8 switching states. And when you would draw the space vector diagram of a 2-level NPC, which you a 2-level VSI, which you had done previously in your course on applied power electronics, and lately you have done very recently in PWM techniques, you know that the space vector diagram, in the space vector diagram, these 8 vectors or these 8 switching states occupy 6 corners of a hexagon, and then 2 states occupy the middle point. Now in the case of an NPC, there are 27 valid switching states, which means that there are too many positions on the space vector diagram, and today we are going to construct the space vector diagram of a 3-level NPC. Now let's go back to the basics of space vector modulation. So again, we have a total of 27 switching states in an NPC, in contrast to 8 switching states that you have in a VSI. Now in a VSI, 6 of these 8 switching states are called active vectors, which occupy the six corners of a hexagon, and then there are two zero vectors that occupy the origin, right? In case of a 3-level NPC, like I said, that there are a large number of switching states, which is 27 in number. These vectors or these switching states are classified into large vectors, medium vectors, small vectors, and zero vectors. Let's first talk about the large vectors. Now, the large vectors in a VSI are those vectors which trace, in one leg the output is either positive, in the other leg it might be positive, and in the third leg, that is plus VDC by 2 plus VDC by 2, and in third leg it may be minus VDC by 2, right? I'm talking about the pole voltage, right? Similarly, another large vector is something like plus, minus, and plus. That means large vectors are those vectors in which none of the pole voltages is zero in any of the phases. So we can make all the possible combinations. We can have minus, minus, plus. We can have 2 plus 1 minus, 2 plus 1 minus, and similarly we can have 2 plus 1 minus, and then we can have 2 minus 1 plus, 2 minus 1 plus, and 2 minus 1 plus. So this is a total of 6 switching states that correspond to the large vectors. Let's do the space vector analysis for any one state. Let's take this state for instance. If I want to draw the pole voltage space vector, it will be 2 by 3 times the pole voltage in phase A plus the pole voltage in phase B at an angle of 120 degrees plus the pole voltage in phase C at an angle of minus 120 degrees. Now for this particular switching state, I know that VAO will be VDC by 2, VBO will also be VDC by 2 but at an angle of 120 degrees, and VCO will be minus VDC by 2 at an angle of minus 120 degrees. If I solve this further, I will get 2 by 3 into VDC by 2 into 1 plus 1 at an angle of 120 minus 1 at an angle of minus 120, that is 2 at an angle of 60 degrees. So for the large vector, the magnitude is 2 by 3 VDC and the angle is 60 degree for this particular vector. Similarly, if you go on calculating the space phasor for all switching states, the magnitude, all large vectors, the magnitude will remain equal to 2 by 3 VDC. However, this angle will keep changing by a factor of 60 degrees. So if you will occupy 6 positions on the hexagon through these large vectors. Now let's try to draw the hexagon. You can also confirm these switching states for the converter. All right, so you have an origin point and you have 1 2 3 4 5 6 numbers of large vectors. So 1 2 3 4 5 and 6. So these are the 6 corners of the hexagon which are occupied by the large vectors. We know that at an angle of 60, we just found out this particular switching state was plus, plus, minus, right? If we do the others, this one over here will be minus, plus, minus. This one over here will be minus, plus, plus. This one will be minus, minus, plus. This over here will be plus, minus, plus. And finally this will be plus, minus, minus. These are complementary of each other, the ones that are opposite to each other. So these are the large vectors whose angle is different, but their magnitude, the maximum magnitude, is 2 by 3 times VDC, which is the largest possible magnitude with a 3-level NPC. Now, apart from the large vectors, you have, I told you there are a total of 27 states. We have still managed only 6 switching states. That means we are left with 21. Now that we are left with 21 states, we should move on to the next set of vectors, that is the medium vectors. Now, which ones are the medium vectors? Again, there are a total of 6 switching states that correspond to the medium vectors. In the medium vectors, one phase is positive, one is negative, and one is 0. So you can have something like plus, minus, 0, or you can have minus, plus, 0, or you can have 0, plus, minus, or you can have 0, minus, plus, or you can have plus, 0, minus, or you can have minus, 0, plus. So again, there is a total of 6 switching states that correspond to the medium vectors. Let's try to solve for any one. Say the first one, plus, minus, 0. The space vector will be 2 by 3 times VDC by 2 minus VDC by 2 at an angle of 120 degrees, and the third is simply 0, so you don't need to add it. If we solve for this one, we will get the space vector being equal to 2 by 3 into VDC by 2 into 1 minus 1 at an angle of 120, that is root 3 at an angle of minus 30. So this goes, this becomes VDC by root 3 at an angle of minus 30. So the medium vector over here, if you see the medium vector, it will have a length of VDC by root 3, and for this particular switching state, the vector will be at an angle of minus 30 degrees. And if you do all the others, their lengths will continue to remain VDC by root 3, which is lesser than 2 by 3 VDC. So it's medium in length, and its angle will keep changing on the space vector diagram. Now, the hexagon was, the biggest possible hexagon was created by the large vectors. The medium vectors will lie along lines, say minus 30, minus 90, plus 30, plus 90, then again plus 150, so on and so forth, right? So these vectors are going to lie along these lines. So these are your medium vectors. This point is, the length of this point is VDC by root 3. You can even simply do 2 by 3 times cos 30, that is 1 upon root 3, right? So this is the medium vector. All the middle points of the hexagon, they will correspond to the medium vectors. So you have a medium vector here, a medium vector here, a medium vector over here, and a medium vector here, and a medium vector over here. This one that we just calculated was plus minus 0. It was at an angle of minus 30. So this one definitely is plus minus 0. Plus minus 0. We can also label, you can find for all these switching states, you can find the corresponding space vector, and then you can mark it on the space vector diagram. For instance, this one over here is plus 0 minus, I'll rub it because I don't have space. So this one over here is plus 0 minus. This one over here is 0 plus minus. This one over here is minus plus 0. This one over here is minus 0 plus. This one over here is 0 minus plus. If you see opposite, the 0 remains at 0, the plus becomes minus, and the minus becomes plus. So there is some symmetries. There are always some symmetries involved in space vector diagrams. Okay, and then I think we have labeled all of these. Yeah, so this one over here is the medium vector minus plus 0. Yeah, so all the medium vectors are also labeled. Now even seeing this, you can you can understand that instead of having just 6 points of the hexagon, by now we have 6 plus 6, that is a total of 12 points. Actually there will be 21, but on the hexagon till now we have found 12 points, which means that the more number of points, the easier is the approximation of the circle, because the sine wave in the space vector domain reflects as a circle, and your main goal is to trace a circle within this hexagon through switching. And if you have a larger number of points, then you can trace it more optimally, even without going for very high switching frequency, because you have more number of data points. You have more sampling of this space vector diagram. Okay, so this was about the medium vectors. Now let's move on to the third category of vectors, that is the short vectors. So the short vectors are, by now we have further subtracted 6 vectors, so now we are left with 15 vectors in total. Out of this, because out of 27 we have 6 large vectors and 6 medium vectors, that is a total of 12 vectors have been accommodated, and now we are left with 15 vectors. Out of these 15 vectors, the small vectors or the short vectors are 12 in number. So they are a total of 12 in number. The short vectors, they will comprise of either the positive and only zeros, or only negative and zeros. For instance, it will be positive and only zeros, so it can be plus 0 0, or it can be 0 plus 0, or it can be 0 0 plus, or it can be plus plus 0 plus 0 plus, or 0 0 plus. So this is 6 states that use only zeros and pluses, or 6 states that use only negatives and zeros, which means only minus VDC by 2 and 0. So it can be minus 0 0, or actually let's do the complementary. The plus sign, let's take it as let's make it 0, and the 0 signs, let's make them negative. So the 0 signs become negative and the plus signs become 0. The 0 signs become negative and the plus sign becomes 0. The plus sign becomes 0, the 0 sign becomes negative, the plus sign becomes 0, the 0 sign becomes negative, 0 sign becomes negative, and plus sign becomes 0. So these are 6 vectors that use only negative and 0 states, and these are 6 vectors that use only positive and 0 states. A total of 12 vectors, and all of these are small vectors. Now why I have written this and this alongside each other, you will just come to know. Let's first draw the space vector, or find out the space phasor or space vector associated with the first state plus 0 0. So it will be 2 by 3 times plus VDC by 2, right? And then everything else is 0. So the magnitude is VDC by 3, and the angle is simply 0, right? So for this particular state, the magnitude is plus VDC by 3, the magnitude is VDC by 3, and the angle is simply 0. So VDC by 3, if this was 2 VDC by 3, this is somewhere in the middle, This is shorter than the largest vector, shorter than the medium vector, somewhere over here. Its length is VDC by 3. So the large vector is 2 by 3 VDC, the medium vector is VDC by root 3, and the small vector, it has a length of VDC by 3, and the angle is 0. So this is the position of the first small vector. Now let's check its complementary small vector. That means the plus becomes 0 and the zeros become minus. This particular vector, if you see, it will have 2 by 3 minus VDC by 2 at an angle of 120 minus VDC by 2 at an angle of minus 120. Let's solve for this. Angle of minus 120 into minus 1, that is 1. So this particular vector also has a magnitude of VDC by 3 and its phase again is 0, which means that these 12 small vectors will occupy only 6 positions. ये दोनों एक ही position occupy करेंगे. These two will occupy the same position, these two will occupy the same position, these two, so on and so forth, which means that each small vector position has a redundancy of 2, which means each position will be achieved through 2 switching states. This is one of the most interesting features of multi-level converters, that there is redundancy in switching states. That means same output is produced by more than one state, depending upon the type of topology and the number of levels. Sometimes a large number of switching states, more than 2 also, can give you the same output, and therefore you always have a choice in switching states to produce the same output, and that choice is used later on to achieve other things, such as reduce the switching frequency further, or to do capacitor voltage balancing. That's for now, that's beyond your scope. But the point is that multi-level converters are associated with the redundancy in switching state. So if you see this switching state or this switching state, both of these are giving you VDC by 3 at an angle of 0. Similarly, these two will also give you a position over here along the large vectors. The small vectors are located along the large vectors, but half of their magnitude. So along the large vector, but half of its magnitude, along the large vector, but half of its magnitude, so on and so forth. Okay, so these are all along the along the large vectors, but half of their magnitudes, and these are your small vectors. They occupy 6 positions, but they are 12 in number because there is a redundancy of 2. If you take this state plus 0 0, this is plus 0 0, and this is also 0 plus becomes 0, and 0 becomes minus, and this is also 0 minus minus. Similarly, this particular state over here is plus 0 plus 0, and it is also 0 0 minus 0 0 minus. Similarly, this state over here is 0 plus 0 0 plus 0, and it is also a minus 0 minus. Similarly, this state over here is 0 plus plus 0 plus plus, and it is also minus 0 0. And finally, you have this one point, this is 0 0 plus, and it is also minus minus 0. This point over here is 0 minus 0, and it is also plus 0 plus, right? So if you see that each of the small vectors is occupied by 2 switching states, you don't need to really memorize it. If you do the space vector diagram, you can easily draw it, and if you're not doing the space vector diagram, I think this data should be available to you anyways. So these are your small vectors, and they are 12 in number, but they're occupying 6 positions on the space vector diagram. So this is 12, and finally you are left with only 3 switching states. 15 minus 12, that is the last 3 switching states, which are your 0 vectors, and they give you a position at the origin. The 0 vectors, of course, are either each leg is plus VDC by 2 plus VDC by 2 plus VDC by 2, or each leg is minus VDC by 2 minus VDC by 2 minus VDC by 2, or each leg is 0 0 0. So the 0 state has a redundancy of 3. In a 2-level VSI, the 0 state had a redundancy of 2, but over here that was 1 1 1 or 0 0 0, but over here it has a redundancy of 3, that is plus 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 minus 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 or 0 0 0. So you have 3 states, plus 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 minus 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 and 0 0 0, giving you the origin or the 0 vector. So this is the space vector diagram of a 3-level NPC neutral point converter. Now the hexagon that you have seen in a 2-level VSI, it has it's the same hexagon, but you can trace it using only 6 points and a 0 vector position, of course with the redundancy of 2, but the positions on the space vector diagram are only 6 plus 1, that is 7. In this case you have a total of 12 plus 6, that is 18, 19 positions. So to trace the same circle in a multi-level converter, 19 positions may be used, or in case of a 2-level VSI, you can use only 7 positions. So it is clear that this converter is going to give you a better approximation. We have already discussed it by seeing the waveforms, this waveform or this kind of a waveform. Of course, a staircase, more the number of levels, more better is their approximation towards a sine wave. That is clear from the waveforms also. But in the space vector domain, by multi-level converters, you mean that you have more positions on the space vector diagram, more number of switching states on the diagram that can help you achieve a better approximation of the circular trajectory. Now if you take up one sector, basically when you do this hexagon, you try to redraw it a bit like this. You make small triangles in it. So the hexagon, the inner hexagon, it is extended to make small triangles. Yeah, I hope I've not missed some point. Yeah, so you extend all its all its vertices or all its corners and make small triangles. And if you observe this if you observe this kind of a waveform, you will see this kind of a space vector diagram. You will see that each sector can then be seen as something made up of smaller and smaller triangles. Let's take up one sector and analyze it. Suppose you have to generate a reference space phasor in a 2-level VSI, and currently you are in some sector at within some certain 60-degree interval, and you have only 3 choices: either switch V1 or switch V2 or switch the 0 vector, right? Depending upon the length of the reference vector, you will then find for how long you have to switch V2, for how long you have to switch V1, and for the remaining time you will of course switch the 0 state. We have already discussed this time and again. But if you now compare the same thing with a 3-level NPC, things are slightly different. The same vertices 2 by 3 VDC will be obtained by the large vectors. So you have large vector here and a large vector here, one state corresponding to this, one state corresponding to this, and then you also have a medium vector. So you have a medium vector over here, again one state corresponding to the medium vector, and along the large vectors, at the middle point of the large vectors, you have the small vectors, and each of these are provided through 2 switching states. So you have the small vectors with 2 switching states. Alright, so now if you observe this diagram, you will see that this one is forming your inner hexagon and this one is forming your outer hexagon. And if you connect the dots, Then every time you have a reference space phasor, the reference space phasor could be of this length, it could be of this length, it could be of this much length, or it can have any phase. So every time you have a reference space phasor, you will see in which small triangle it will lie. So if it is lying here, you will trace between these three states. But if it is longer, say it is lying here, you will trace between the closest three states. And if it is lying here, of course you will trace between the closest three states. So you have more choice in terms of switching states. Suppose your reference space phasor is lying in the inner triangle, then you will switch the small vector, the medium vector, and the other small vector. Let's switch the small vector, this one, for time, say ta. The medium vector, let's switch it for time tb, and this third vector, let's switch it for time tc. In this case, you never had multiple choices in a two-level converter. You were always had to, in a particular sector, you always had to choose between only these states. But in case of a multi-level converter, and that's just 3 level, if you have more number of levels, then it's an even bigger space vector diagram and even more number of choices. But in this case, you have, every time, depending upon the length and the position, the phase angle theta of the space phasor, you can choose the triangle of your choice, and then you can choose the small triangle of your choice, and then you can accordingly choose the the states to be switched. Now suppose you have your reference space phasor is somewhere lying in the middle triangle, and you have to switch this state for ta, and this state for tb, and this state for tc. So you can simply write, if you switch the small vector, this particular small vector, so you will switch vdc by 3 for the time interval ta. It has to be a vector sum, v1 t1 plus v2, that is the medium vector, that is vdc by root 3 times, it's a vector sum, so you also have to take care of the angle, it's a phasor sum actually. So this is 30 degrees, and it is switched for the time tb. And then you have the third state, that is tc, which is again a small vector, so its length is vdc by 3 again, and its angle is 60 degrees. Angle of this one, right, is 60 degrees. So 60 degrees, and this is switched for tc, and all this combined should be vref at an angle of theta, whatever your theta is, this is your theta, switched for a total of ts. You also know that ta plus tb plus tc is equal to ts. You can choose the switching frequency of your choice depending upon your wish, and of course as you go into higher and higher number of levels, you choose a larger and larger ts, or you can say smaller and smaller fs, smaller and smaller switching frequencies, because now that you have more number of data points, you don't need more number of higher switching frequency. In this case, you had to go for higher switching frequency because the sampling points were not many. Okay, so ts, you have chosen ts. Now you have to find ta, tb and tc. You have a reference space phasor. What is the reference that you want from the converter? You know the DC available DC voltage. So what is unknown is ta, tb and tc. And in terms of ts, of course, you have two equations, t8 plus tb plus tc is equal to ts, and you have an equation v1 t1 plus v2 t2 plus v3 t3 is equal to vref ts, of course in the complex domain. You just equate their real and imaginary parts. Equating their real parts, you will get one equation. Equating their imaginary parts, you will get another equation, and this is your third equation. 3 variables and ta, tb, tc, and 3 equations. So from this equation you will get a real equation and a complex equation, equating their real parts and equating their complex parts. So you'll get 2 equations from here, 1 equation from here, and you can simply find out the values of the time intervals for which each state has to be switched. So I can just write that for you. So ta over here is ts into 1 minus 2 MA sine theta, where theta is the angle of the reference vector with respect to your baseline or your reference line. TB is TS at an into 2 times MA sine of pi by 3 plus theta minus 1, and of course theta varies only between 0 to 60 degrees in each sector, and then TC is equal to TS 1 minus 2 times MA sine of pi by 3 minus theta, where MA is your modulation index, which is root 3 Vref, what is the desired output from the converter, divided by VDC, what is the input of the converter, right? So this gives you the dwell times or the timing calculations for a 3-level NPC. That was all for today, and I hope it is clear to you that using a multi-level converter, you just move from 2-level to 3-level. I mean, you can go up to 5-level, 7 level, 9, 11, so on. There's no end. So just by moving from 2-level to 3-level, you saw that how many points you got on the space vector diagram, and how easy it is to trace a circle within the hexagon, because there are too many points within the hexagon. So each point is much closer to a circular trajectory than than it would have been in a hexagon with only six corners. Now you have points within the hexagon there, and even on the hexagon you have more points. So it's always easier to trace that circle or to trace that sine wave with more number of points, and therefore even with a lesser searching frequency it is possible. So that's all for today. If you have any doubts or queries or questions, please feel free to ask me. That's all. Thank you very much.